Hey everybody, today we're going to be talking about interpreting derivative graphs. So we're going to kind of be formalizing the idea of what it means when a derivative is positive, what it means when a derivative is increasing, what it means when a function is increasing or concave up, what does it mean for a second derivative to be positive or negative. Now we've talked about these things in the past, but we're going to kind of summarize everything and make sure we understand it through a graphical sense and then through an analytical sense. So with that said, let's go ahead and get started. So the first thing we want to look at is the graph of f. And we want to graph f prime and f double prime. Now we've had plenty of practice with this idea in the past, but let's go ahead and take a look at this graph of f. And you can see in the lesson to the left there, probably a little bit more better graph of what this looks like. We have something that looks like this. Here at the end, this is -8. This low point here is -4. This point here is -2. This point is 4. This one is 9. And then this is 14. So this is the graph of f. And we're going to go ahead and graph f prime and f double prime. So let's go ahead and take a look at the graph of f prime. And I'll do it right underneath it just so that we can compare it. Now, if we're looking at f prime, what are we looking for? Well, when I go to graph a derivative function, I look for three main things. Number one, I look for when the derivative is supposed to be 0. And if we're looking at the graph of f, we can see that the derivative is 0 anytime that f has a horizontal tangent line. So when x equals -4, we can see a horizontal tangent line there. So I'm going to go ahead and at -4, that means that there's going to be a 0 for the f prime graph. And at x equals 0, I know I didn't graph this perfectly, but if you look at the lesson to the right, it's a little bit easier to see, or it's a little bit more clear, that we have this, this maximum, you would say, at 0. So we have another horizontal tangent line at 0. We have a horizontal tangent line at 9. So there, we've determined where f prime is supposed to be 0 based on horizontal tangent lines. The next thing I look at is I look for where f is going to be increasing and where f is going to be decreasing. And we'll summarize this a little bit more later. But what we observe from -8 to -4 is that f is decreasing, which implies that f prime is going to be negative. Because if f is decreasing, that means its slope throughout that interval is negative. And that's what the derivative is. It's the slope of the curve. So we can see that this graph is decreasing. Therefore, this is going to be negative. Now, I don't necessarily know where exactly, so I'm just going to kind of circle the negative area, and we'll go back to that later. From -4 to 0, we see that f is increasing, so we have positive. From 0 to 9, it's decreasing. F is decreasing, so f prime is going to be negative. And then from 9 to 14, we can see that f is increasing, so f prime will be positive. So that's the first idea that we can talk about here, or understand. Okay? The second idea is the idea of steepness. And I always ask this question, where is the graph of f steepest? Well, the graph of f is steepest on the interval -8 to -4. It's actually steepest at the beginning here at -8. Since it's steepest, that means f prime will be at its least value at that point, okay? And then we can see that the slope is kind of, or the function is kind of flattening out. That means the slope is going towards 0. So it's going to look something like this, okay? And then where is it steepest from -4 to 0? Well, we can see that it's steepest at that point right there. It is climbing at the steepest rate, or at the greatest rate. So we could say that since f is steepest at -2 in that interval from -4 to 0, we have a high point on the graph of f prime. So at -2, we have a high point, okay? And then it's steepest from 0 to 9, we would say it's steepest at 4. So here's 9, and then 4 is 4 is here. Now this is not drawn to scale at all, but we can see that it's steepest at 4, which means it's going to be the lowest point there. So it's going to come up and then down, and then it's got to go down to the lowest point on this graph because it's the steepest point there. And then it starts to flatten out again, which means the derivative is going back towards 0. Okay? And then we can see that from the interval 9 to 14, the steepest point is actually at the end at 14. So at 14, we would have the highest point there. So we have something that might look something like this. Okay, this is not exact, but it's rough. Okay. Now, one thing I want to emphasize, and we've talked about point of inflections in the past. A point of inflection on the graph of f is where f changes concavity. So we're going from concave up to concave down when x equals -2. So we have a point of inflection here. Well, if we look here, we can see that f has a point of inflection when f prime has a maximum there. Or we would say when f prime changes from increasing to decreasing. We also have another point of inflection at 4 because f is changing from concave down to concave up. So at 4, we have another change in direction on f prime. So there's the graph of f prime. Let's go ahead and take a look at the graph of f double prime now. And just kind of getting a practice with graphing derivatives, but at the same time trying to see relationships between the function, its derivative, and its second derivative. So we, again, are looking for when f prime has a horizontal tangent line. So we can see that f prime has a horizontal tangent line at -2. So that means f double prime will be 0 there. It has a horizontal tangent line at 4. So it hits 0 there. Now, depending on what's going on, we don't really know exactly what's going on here at the end. So this may be a point of inflection, or it's not really a point of inflection because it's an endpoint, but if we knew what was beyond x equals 14, or if this graph continued beyond this domain, we don't know if this is changing concavity at 14, or if it's just getting steeper, or if it's staying like at a constant rate. So we don't really know what's going on here. So this is an assumption that kind of curves like this. It may not necessarily. But anyways, we can see from -8 to -2 that f prime is increasing, so f double prime will be positive. From -2 to 4, it's decreasing, so will be negative here. And then from 4 to 14, it's f prime is positive, so f double prime will be, f prime is increasing, so f double prime will be positive. So we get a graph that looks something like this, or our graph must reach those intervals. And again, looking for steepness, the steepest point from -8 to -4 is found at -8. So that means that would be the highest point in that interval. And by the way, these are going to be open intervals here. And then from -2 to 4, f prime is decreasing, so it's going to be negative. But the steepest point in that interval, it's kind of hard to say. We can't really say for sure. But we would maybe say here might be the steepest, so that might be the lowest. Okay, somewhere in there. So we'll put a low point here. And then we see that we have maybe a point of inflection at 9. I don't know, maybe not. We don't really know what's going on exactly at that point. But we have a graph, and then at 14, maybe it looks like it's flattening out, but again, we don't know what's actually actually happening at the end. So we're just going to kind of do a little rough graph of f double prime. But looking for some key features along the way, trying to see how these things are related here. So again, we see that when f is increasing, f prime will be positive. When f is decreasing, f prime will be negative. We see that when f is concave up, so from -8 to -2, and from 4 to 14, when f is concave up, we see that f prime is going to be increasing over those intervals. So from -8 to -2, concave up, and f prime is increasing. And then from 4 to 14, concave up, so f prime is increasing. But now we go down to the second derivative. We see that when f is concave up, f double prime will be positive. So f double prime is above the x-axis from -8 to -2. We see that f is concave up there. F is concave down from -2 to 4. So we see f double prime is negative from -2 to 4. And we see that f is concave up from 4 to 14, so f double prime will be positive from 4 to 14. So again, when f is concave up, f prime is increasing, f double prime is positive. When f is concave down, f prime is decreasing, and f double prime is negative. So there's all these different things going on here. When f has an extrema, some sort of relative extrema, we can see that f prime is changing signs. So it changed signs at -4, 0, and 9 because f is, has a relative extrema. It's changing directions at -4, 0, and 9. Okay? When f has a point of inflection, so at -2 and 4, we can see that f prime is changing directions at -2 and 4, and f double prime is changing signs at -2 and 4. So seeing these connections here is a valuable tool in calculus, and that's where the chart really comes in handy, really comes in play in understanding how these relationships work. Now, you can see in the lesson over to the left, you can see that my f prime graph actually just continues going upwards, because maybe I was making an assumption that there would be a point of inflection here on this graph, but I wasn't making that same assumption on the lesson. Either way, we don't really know what's going on at the end here. But if this is continually getting steeper, then this graph is going to continually increase instead of returning back to 0. But you can generally see an idea here, if you want to look at it this way. This is going to be x to the 4th if these just continue upwards. Let's assume they continue upwards. If they just continue upwards, then this is x to the 4th function, which means this should be an x to the 3rd function. So it should go up and then down and then up again, and it should kind of just keep increasing past that point if we were to assume that this is x to the 4th. And since this is a cube function, the derivative of that would be a square function, and so we would have it come down and then back up again. So it would look something, oops, wrong color here, something like a parabola, because that's a cube function. So something like that, okay? So however you graphed it, we're just looking for points of inflection on this graph to see when f double prime changes signs. We're looking for extrema on this graph to see where f prime is changing signs, okay? So from there, I want to really emphasize this idea because students tend to struggle when it comes to justification. There's two things that they really struggle on when they're trying to interpret the relationships here. And so the first thing is that they always use the word it. It is not a proper pronoun. It doesn't describe what we're talking about. We want to make sure that we're identifying which function we're talking about. So we would say that f is increasing when f prime is positive. And I get a lot of this from students. Well, f is increasing when it is positive. Well, what is it? If f is it, then you're saying f is increasing when f is positive. That's not a true statement. F is increasing when f prime is positive, and so on. So we really want to make sure that we understand the difference between the idea of being positive and the idea of increasing here, okay? So what's the difference between positive and increasing? Well, positive simply means that the function is above the x-axis. It's a positive number, right? When I say function is increasing, though, what we're saying is that the function is going in an upward trend. It's going from left to right. You can see that the graph is going uphill. Like if we're on a roller coaster and we can only go from left to right, from lesser numbers to positive numbers, the function is increasing when you see it going uphill. It's decreasing when you see it going downhill. So please be careful when you're justifying things, that when you say positive, you actually mean above the x-axis. And when you say increasing, you mean that the function is going uphill. And then same thing if the function is negative, you mean below the x-axis. When it's decreasing, you mean that the function is going downhill. Again, relationships. This function is increasing when this function is positive. Okay? This function is concave up when this function is increasing and when this function is positive. Okay, and that's where the chart really comes in handy to see. Okay, so in this graph, just looking at it real fast, where would we see that f is positive? F is positive over the interval for which it's above the x-axis, for which f is above the x-axis. So we can see from a to 0, the graph is above the x-axis. And then we'd say f is increasing, it's going uphill, actually over two intervals here. We would say that it's increasing over the interval a to b and the interval c to d. So please just be careful when you're interpreting things in that manner. All right, so let's go ahead and take a look at the graph of f prime, which is a little bit different than this one, but very similar. Okay, this is the graph of f prime now, and we want to answer some questions based on the graph of f prime. Okay, so in the first case, we're asking, when is f increasing? Okay, again, pay attention. This graph is f prime. We're not looking at f. So this is where the chart is really helpful. Let me give you some justification here. We would say, for part A here, we would say that f is increasing when f prime is positive. So when we're going to justify something, or when we're looking to interpret what's going on, you look at what's asked for. It's talking about, or it's asking about the function f. So we want to know something about f. Now we look at what they gave us. They gave us a graph of f prime. So we want to interpret their question in light of what they gave us. They're asking about f, but they gave us f prime, so we want to make sure that we're answering it in light of f prime. So f is increasing when f prime is positive. We see that the graph of f prime here is positive when it's above the x-axis. So we would say from -7 all the way to 2. From -7 all the way to 2. Now, you might say, well, what's going on at -4? When x equals -4, f prime is 0, so how is f increasing? Well, the definition of a function increasing is for every value within a closed interval, if the next point is above the previous point, it is increasing. So at x equals -4, the point just to the right of that, so like -3.9999, the function is a little bit higher than it. Okay? So when we answer increasing functions, we always talk about closed intervals. And if we're going to write a closed interval that looks something like this, -7 to -4 in the closed interval, and then we'd also say that f is positive from the closed interval -4 to 2, well, this, because it's a closed interval, it's in a union, we can also just conclude that that is from -7 to 2 as a whole. Okay? So for question B, when is f decreasing? Well, let's go ahead and justify that according to the graph that they gave us. We would say that f is decreasing when f prime is negative. Okay, so we are looking at the f prime graph. We're looking to see where that graph is below the x-axis, and we can see that it is below the x-axis over the interval 2 to 5 there. So f is decreasing when f prime is negative, or we could actually clarify that a little bit, when f prime is less than or equal to 0, so from 2 to 5. Now let's go ahead and look at part C. We're looking for local extrema. Well, local extrema occur when a function changes direction. When f changes direction, we have a local extrema. Maybe it's a local minimum or a local maximum, but we have a local extrema. So think about this. If f is changing direction from increasing to decreasing, we'll have a relative maximum. But let's see what that looks like in terms of the f prime graph. F changes direction when f prime changes signs. Okay, so that's a really important concept there. We have an extrema on f when we see that the function changes from increasing to decreasing, or from decreasing to increasing. So when does a function change from increasing to decreasing? When its derivative changes from positive to negative. Or, for a local minimum, when f changes from decreasing to increasing, when f prime changes from negative to positive. So in this graph, let me highlight it here. In this graph, we can see that at -4, at x equals -4, we have a local, actually we don't have anything going on there because again, this is f prime. At -4, the derivative, f prime, is going from positive to 0 back to positive again. So the derivative never actually changed signs there. It went from positive to positive, which means the function went from increasing to a horizontal tangent line to increasing again. So there is no relative extrema at -4. And then we would say that there is a relative extrema at 2, okay? Because there is a relative extrema at 2 because f prime is changing from positive to negative. So let's justify that a little bit here. We would say that f has a local extrema. Let's be more specific. F has a local, what is going on here? Well, f prime is changing from positive to negative here. So f has a local maximum when f changes from increasing to decreasing. Okay, and now we need to interpret that in terms of f prime. Well, f changes from increasing to decreasing when f prime changes from, well, f is increasing when f prime is positive, and f is decreasing when f prime is negative. So we can see exactly that on the graph that's given here. We can see at 2, we got this going on. Okay, this is 2, and this is the graph of f prime. We can see that f prime is changing from positive to negative, which means that f is changing from, at 2, it's changing from increasing to decreasing, which means we have a relative maximum at that point. Okay, so we have a local maximum at x equals 2. Now, in the lesson, it shows that there's a local maximum at -7 and 5. Well, why is that? Because at -7, you'll notice that the interval is a closed interval. And at 5, you also have a closed interval. So this interval being from -7 to 5 means that these points exist. And we can see, we can justify a little bit here, that at x equals -7, we see that f prime, for every value from -7 on, is positive, which means that f is going to be increasing in that interval. Well, at -7, here's x equals -7, the function, f prime is positive, which means f is increasing, making this a lower point than all its surrounding points, so it's a local minimum. Over on the other side of things, when you're looking at x equals 5, we can see, here's x equals 5, f prime is negative. Okay, so if f prime is negative, that means f is decreasing. So if f is decreasing to x equals 5, we can see that there is a relative minimum there. Okay? All right, a little more questions here. Part D, where do inflection points occur? Well, it's all about interpreting based on the chart. It's very helpful. But where do inflection points occur? We would say that f has a point of inflection when f changes concavity. Okay, that's basically what we're looking for here. But again, we're not looking at the graph of f. We're looking at the graph of f prime. Now, we've gone through the whole process of developing this, so I'm going to go ahead and justify this according to how we feel comfortable. F changes concavity when f double prime changes signs. So that means either from positive to negative or negative to positive. But now we got to go over to our chart and interpret it according to the f prime graph that was given here. So if f double prime is changing signs, that implies that f prime is changing changing direction, okay? So let me write the chart here. I know it's off to the side, but I want to be able to point to it right now. We have these graphs, or we have these relationships here. This is the graph, the column for F, F prime, and F double prime, okay? And we would say that F is positive or negative, F prime is positive or negative, F double prime is positive or negative. F is increasing or decreasing when F prime is positive or negative. And then F is concave up slash down, and this would be increasing slash decreasing. So you can see that we have all these three are the same things, these two are the same things, and this thing is alone down here. So we can see that F has a point of inflection when F changes concavity. So if we're changing from concave up to concave down, then that's the same as saying F double prime is changing from positive to negative, and then vice versa, or when F prime is changing from increasing to decreasing, or vice versa. So I would say that this row here is identifying when this changes, when this row changes, we have a point of inflection on F. When this row changes, we have relative extrema on F. Okay, so when this row changes, we have relative extrema. So this helps us understand things. F has a point of inflection. F has a point of inflection when it changes concavity. But we can also interpret it one of these two ways. So either F prime is changing direction or F double prime is changing signs. Since we're looking at the F prime graph, we're looking at this. When does F prime change from increasing to decreasing, or from decreasing to increasing? And we could see on this graph here, we can see it changes direction at x equals -4, x equals 0, and x equals 3. Okay? All right, and the last question here is identify the concavity of F. Well, again, oops, let me keep this here so I can point to it. Okay? We would say that F is concave up when, well, let's look at the chart. F is concave up when F double prime is positive, or when F prime is increasing. Since we're looking at the F prime graph, we're going to be looking at this guy. So we would say F is concave up when F prime is increasing. Okay? And so we can see that F prime is increasing, meaning going uphill. We're looking at the F prime graph. F prime is increasing from -4 to 0 and from 3 to 5. Okay? So from -4 to 0 and 3 to 5. Okay, so that's when F is concave up. And then we can finish this off by saying F is concave down. F is concave down when F prime is, again, F is concave down when F prime is decreasing. Okay. So on our F prime graph, we can see that F prime is decreasing when it's going downhill. So from -7 to -4, and from 0 to 3. So therefore from -7 to 4 and 0 to 3. So that's our final answer on either. Now some, again, might say, why is F increasing over a closed interval, but it's concave up over an open interval? Well, that has to do with the definition of increasing and decreasing versus concave up and concave down. But to keep it simple, just to help you get the right notation down, anytime a function is increasing, it's always over a closed interval as long as all those points are within the domain that we're talking about. And the function is always concave up or concave down over an open interval. All right, so that's an example of what it looks like on a graph. Okay. Now let's go ahead and look at a little bit more a little deeper to make sure we're good with this. Okay. So notice in both of these graphs that I gave you on the lesson that in number 1, I gave you the graph of F. And in number 2, I gave you the graph of G prime. So we need to make sure that we're interpreting and looking for the proper things based on the graph that was given. So looking at each part of these, part A, it says, where do extrema occur and what type? Well, extrema occur, remember, extrema occur when this row changes signs, and points of inflection occur when this row changes signs. So we would say, where do extrema occur? Extrema occur when you observe the graph of f changing from increasing to decreasing or decreasing to increasing. In other words, when f is changing direction. Or you could say that extrema occur when f prime changes signs. Well, again, it depends what graph you're looking at. So I would say that f has extrema when f, what's given, f has extrema when f changes direction. So we can see pretty easily here that extrema occur at 0 because f is changing from increasing to decreasing, at 2 because f is changing from decreasing to increasing, at 4 because f is changing from increasing to decreasing, and at 6 because f is changing from decreasing to increasing, okay? So for option A, for the graph of f, or for, not option A, but for question A, looking at the graph of f, we can see extrema here, 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 and here. But if we answer the same question for number 2, when does G have extrema? We're looking at G prime here. So we would say G has extrema when G prime changes signs. So both of these graphs look exactly the same, but we're looking at different functions here. So G has extrema when G prime changes signs. So we can see that G prime changes signs at 1 point, like 1-ish there, and that's it. So there is no change in signs anywhere else. It did not change signs at x equals 4. So we would say that G has an extrema when G prime changes signs, which is at 1-ish. Okay. So for question B, it says where does the function f and g increase and decrease? Well, f increases, right? F increases when f prime is positive. Okay, that's a good relationship, but we're looking at the graph of f. So when is f increasing? F is increasing when we see it going uphill. So from -2 to 0, and from 2 to 4, and then from 6 to 9. That's when f is increasing. F is decreasing from 0 to 2, and from 4 to 6. But if we look at this graph, the graph of G prime, we would say that G is increasing when G prime is positive. So G prime, this is the graph of G prime, it's positive from -2 to 1-ish, and that's it. So we would say G is increasing from -2 to 1, and then we'd say that G is decreasing from 1 to 9 because G prime is negative. For C, we would say, where is f concave up? Well, f is concave up when f is concave up. F is concave up, we'd say from 1-ish to 3. We can see that it's concave up here. And we can see that it's concave down, concave up from 1 to 3 and also from 5 to 9. Okay? And then we could say that f is concave down from -2 to 1, and then from 3 to 5, because we're just looking at f, the graph of f, where is it concave down? Again, concave down like a frown, concave up like a cup. But looking at number 2, G prime, when is G concave up? G is concave up when G prime is increasing. So we would say that G prime is increasing from -2 to 0. Therefore, G is concave up. We would see G is concave up from 2 to 4 and from 6 to 9 also because G prime is increasing. And then we would say that G is concave down. G is concave down when G prime is decreasing. So G is concave down when G prime is decreasing. So from 0 to 2 and from 4 to 6. And then where is there a point of inflection for each of these? Well, a point of inflection occurs when f changes from concave up to concave down or from concave down to concave up. So we could see that happening at 1-ish and at 3 and at 5. We can see a change in concavity. But when we're looking at G prime, we would say G has a point of inflection when either G changes from concave up to concave down, or in our case, G prime changes from increasing to decreasing. So we would say that G has a point of inflection at x equals 0, at x equals 2, at x equals 4, and at x equals 6. Okay? So again, it's very important that you understand what the question is asking for and then interpret that in light of the graph that was given. And this chart really helps us understand that relationship. Okay? So now let's go ahead and look at some analytical questions and answer the questions in the same way, but in the light of functions. So for number 1 here, it says that f of x is equal to 2x cubed minus 14x squared plus 22x minus 5. So the graph of f of x, or the function f of x, is given. We want to know, where do extrema occur and what types? Well, extrema occur, according to the chart, extrema occur when f changes direction, or when f prime changes signs. So we need to take the derivative here. F prime of x is equal to 6x squared minus 28x plus 22. So that's my derivative function. We are looking for relative extrema on f, which means we're looking for when f prime changes signs. So the first thing I'm going to do is factor f prime, so I have a nice clean function to work with. I can factor a 2 out of all those. So I got 2 times 3x squared minus 14x plus 11. And then we can do some quadratic factoring here. So f prime of x is equal to 2 times, let's see, it's going to be 3x and x for the first term, because that's prime. 11 is prime, so I know it's going to be 11 and 1, and I want a negative 14, so that would be negative and negative. So there's our factored form of f prime. Remember, extrema occur when f prime changes signs. Well, f prime can only change signs if at a point if it is a critical point. How do we find critical points? Critical points are when f prime equals 0, f prime does not exist, and endpoints. Well, there are no endpoints because there's no interval. F prime always exists because this is a polynomial. So the only thing we have to look for is when f prime is equal to 0. So we'll set f prime equal to 0, and then we'll solve this. So this is when x equals 11 thirds and 1. Okay? So those are our only 2 critical points here. Critical points are x equals 1 and 11 thirds. So now we're going to set up a number line. This is all just good practice in a day. 11 thirds. So we would say that f prime of x is 0 at these 2 points. So we'll pick points on either side of those. If I plug in a 0, because I'm looking for the interval from negative infinity to 1, if I plug in 0 to the factored form, I've got a positive times a negative times a negative. So this interval we would see is positive. We plug in a value between 1 and 11 thirds. Well, 11 thirds is 3 and 2 thirds. Sorry, 3 and 2 thirds. So we'll pick like 2. If I plug in 2, we got a positive. 3 times 2 is 6, so 6 minus 11 is a negative. And then 2 minus 1 is positive. So positive, negative, positive. So this is a negative here. And then any value greater than 11 thirds, so like, I don't know, 10 is fine. If I plug in a 10 here, I get positive, and then there's a positive out front, so positive. So we can see that f prime is positive, negative, positive. Well, that means that f is increasing, then decreasing, then increasing again. So we can conclude that we have a relative maximum when x equals 1, since f prime changes signs from positive to negative. And then we can also conclude that we have a relative minimum when x equals 11 thirds here, because we can see that f prime is changing from negative to positive. Okay, since f prime changes signs from negative to positive. Okay, so that is our relative extrema, or where they occur at least. Okay, so for B is asking for when f is increasing or decreasing. Well, that's all the same justification here. F is increasing when f prime is positive. So we would say, let me use a different color here. F is increasing from over negative infinity less than x less than 1 and 11/3 less than or equal to x less than infinity, since f prime is positive. Running out of room here. Okay, and then we can also say that f is decreasing over 1 is less than or equal to x less than or equal to 11/3, since f prime is negative. All right, so that answers B for us for question number 1. So f is increasing when f prime is positive, f is decreasing when f prime is negative. We're looking at the f prime number line. This is all just good practice here. Remember, this is not justification. This is only a good way to see what's actually happening. It used to be good justification years ago, but it's no longer. Okay. So now if I'm looking at question C, it says where does f and g have concave, where is f concave up and where is f concave down? Well, f is concave up when, looking at the chart, we could say f is concave up when f prime is increasing or when f double prime is positive. I cannot look at an analytical function and see when that function's increasing. I just can't see when it's increasing. I can only see when it's positive or negative. So when we're looking at functions, we want to always get down to a sign change or sign values, positives or negatives. So we don't really care when f prime is increasing. What we care about is when f double prime is positive. So let me get back up here to our f prime function. So we would say f is concave up when f double prime is positive. So f double prime of x is equal to 12x minus 28. And we know when f double prime is positive, well, we got to go through the motions again. We got to set f double prime equal to 0 and then solve that. So we got 28 equals 12x. So x equals, what is that, 4? That'd be 7/3. Okay, so we can set up another number line here, and we can see at 7/3 for f double prime of x that there is a 0. So f double prime is 0 at 7/3. So we'll pick a value to the left of that. Maybe we plug in 0. So if I plug in 0 to f double prime, I end up with a negative value. And if I plug in, let's say 10, 12 times 10 is 120, minus 28 is a positive value. So we can see pretty easily where f double prime is negative and positive. So we can conclude, and I always like doing this, adding a little bit to this so we can see what's going on. If f double prime is negative or positive, we can see that f of x is going to be concave down and then concave up. So that's just a good way to see it if you're going to add rows to this number line here. So let's go ahead and justify this. We would say that f is concave up over 7/3 less than x less than infinity, since f double prime is positive over that interval. And then we'd say f is concave down over negative infinity less than x less than 7/3, since f double prime is negative. Okay, so we've answered question C there. We know where f is concave up and concave down. And the last part, question D, it says, where are there points of inflection? Well, again, that's the last row of our chart. F has a point of inflection when f changes concavity? Well, that means f double prime has to change signs. So we can see that f double prime changes signs only at one point here. So let me use a different color. We would say that f has a point of inflection when x equals 7/3, since f double prime changes signs. Okay, so that answers question number 1 in pretty good detail. And then we can take this information and actually graph f pretty easily now. We know where it has relative max and mins. We know when it's increasing, decreasing. We know when it's concave up and concave down. We know when there's points of inflection. So calculus actually helps us determine the look of a graph pretty nicely. Okay? So now let's take a look at question number 2. And we're looking at question number 2. Again, what's given to us? We are given g prime. We're not given g here. So we're given the first derivative already. So g prime of x is equal to x minus 1 squared times x minus 4. So there's g prime. And it's already factored for us. So this makes it a lot easier to deal with. So question A, where do extrema occur? Extrema occur when g prime changes signs according to the chart. So we have to figure out where g prime changes signs. So the first thing we have to do is figure out where it's 0 and does not exist. We have to find the critical points. So we'd set the function equal to 0. And we can see that g prime is 0 at 1 and 4. So those are some of our critical points. Again, our critical points are when g prime is 0, got those. When g prime does not exist, well, g prime always exists because, again, it's polynomial. And at endpoints, there's no interval here, so there are no endpoints. So our critical points are 1 and 4. So now we'll set up a number line, just like we did before. This is the number line for g prime. At 1 and at 4, g prime has zeros. And then we're going to go ahead and plug values in to the left and right of each of those points. If I plug in x equals -1, for example, -1 minus 1 is -2 squared. That's a positive. And then -1 minus 4 is a negative. So this is going to be a negative here. If I plug in a value between 1 and 4, let's say 2. 2 minus 1 is positive. Squared is positive. 2 minus 4 is negative. So again, a positive times a negative is a negative. And then if I plug in a 5, 5 minus 1 is 4. Squared is positive. 5 minus 4 is 1, so that's positive. So positive is positive. So you might be asking, why is there a sign change or why did g prime not change signs at 1? Well, the reason is because that critical point of 1 came from this part of the function where we were squaring. And when we square something, it's always positive, okay? So we didn't have a sign change here. So let's go ahead and write our justification here. We would say that g has what? Well, here at x equals 1, g prime is negative, which implies that g is decreasing and then decreasing again. So there is no relative extrema at 1 because g prime did not change signs. But we can see that g prime changed signs from negative to positive, which means g changes direction from decreasing to increasing. So g has a relative minimum when x equals 4, since g prime changes signs from positive to negative. Okay? And then, so that's A. If we're looking at B, B is related. It says, when is G increasing? Well, G is increasing. Let's justify this in our brains before we write it down. G is increasing on the chart when G prime is positive. So G is increasing over 4 less than or equal to x less than infinity, since g prime is positive, and then g is decreasing. G is decreasing over negative infinity less than x less than or equal to 4 since G prime is negative. That's the simplest way of justifying it, you would say. So again, you'd say, well, G prime isn't negative at x equals 1. You're right. The technical definition is G is decreasing when G prime is less than or equal to 0, not just negative. So that might be a better way of saying that. But that's the justification for A and B. Now let's go on to C. When is G concave up and concave down? Well, G is concave up when G double prime is positive. So we've got to go back to the drawing board and figure out what G double prime is before we go any further. There's a couple ways of figuring out G double prime here. We could expand all this and then put it in standard form and then take the derivative by just using power rules, or we can use the product rule here with the chain rule. So the derivative is just good practice, I guess, to use the product rule. We've got the first term there. We've got the second term there. This is a pretty easy product rule. The derivative of the first thing using the chain rule would be 2 times x minus 1 to the first times the derivative of the inside. The derivative of the inside is just 1. So that's the derivative of the purple part times the blue part, so times x minus 4. And then plus the derivative of the second part, which is 1, times the first part, so times x minus 1 squared. And then from here, we'll go ahead and expand this all and simplify it all. So we get G double prime of x is equal to 2 times x squared minus 5x plus 4. And then this guy just expands to x squared minus 2x plus 1. And then do a couple more steps here to make sure I'm not making any mistakes. That's 2x squared minus 10x plus 8. And then plus x squared minus 2x plus 1, just FOILed or distributed there. And then combine like terms. So G double prime of x equals 3x squared minus 12x plus 9. Okay, so now we're looking for when G double prime is positive or negative. So we have to set that equal to 0. So we'd say 0 equals, actually before we do that, let's go through the motions of factoring here. So G double prime of x, factor out of 3. So that'd be 3 times x squared minus 4x plus 3. And then that factors further to 3, oops, I should say x squared. 3 times x minus 3 times x minus 1. And now we'll set this equal to 0. And then we can see that that occurs when x equals 1 and 3. So since we're looking at G double prime, technically we wouldn't call them critical points, but we would call them points of interest. Well, that's at least what I call them. The points of interest are when G double prime equals 0. So we'll set up another number line here. At 1 and at 3, G double prime is 0. So we'll check the signs in between each one of those intervals. If I plug in 0 over here, if I plug in 0, I get a negative and a negative. So this is going to be positive here. If I plug in 2, I get a positive 3, a negative value, and a positive value, so that'll be negative. And if I plug in 4, that'll be positive, positive, positive. So again, a positive value. So we can see pretty easily G double prime, the signs of G double prime, which implies the concavity of G. So G is concave up, concave down, concave up. So again, it's all about writing out what you're saying, not just doing number lines. So we would say G is concave up over the interval negative infinity less than x less than 1, and 3 is less than x less than infinity since G double prime is positive. And then G is concave down. G is concave down over the interval 1 is less than x less than 3 since G double prime is negative. Okay, so that answers the question for part C. And then the last question we have is, where does G have a point of inflection? That's the last row again. G has a point of inflection when G changes concavity, when G prime changes direction, or when G double prime changes signs. Since we're looking at analytical methods, we want to look at a sign change. So we can see that G double prime changes signs at 1 and 3. I'm running out of room here, so I'll go ahead and write this off to the side here. G has a point of inflection when x equals 1 and 3, since G double prime changes signs. Okay, so that was a lot of good analytical practice as well as graphical practice when it comes to interpreting derivatives, interpreting what derivatives mean and what second derivatives mean for a function. So I hope that really helped you out in understanding the relationships between these things using calculus. So stick around for the next lesson, and I'm excited to see you back.